Hi. This video is a review of today's classwork from November 16th, and it's also the material to help you with the classwork for tomorrow, the 17th. Okay, so the first thing, I'm just going to put this classwork right in front of the camera here. The first question says, let me see if I can focus this a little better. I guess not. It says the diagram below shows the relative positions of the Sun, the Moon, and the Earth when an eclipse was observed from Earth. Positions A and B are locations on Earth's surface. Which statement describes the type of eclipse that was occurring and the position on Earth where this eclipse was observed? And so the answer was 3. A solar eclipse is observed from position A. Okay? Because Sun, Moon, Earth, that lineup will give you a solar eclipse because the moon will block out the sun on this one little spot on Earth. Okay. Next, question 2 and 3 refer to this graph which shows tidal changes. And the question 2 says, which inference about tides can you make from this graph? And the answer is choice 4. Okay, that the tidal change is cyclic. Okay, it's a cycle, and it's predictable, and it's a repeating pattern that you can see happening over and over. Question 3, according to the pattern shown on the graph, the next high tide will occur on the following day at what time? The first high tide occurred here. If you look, it's hard to see on this paper right now, but you should have the paper in front of you. It happened at around 1 a.m. That was high tide right there. And then the next high tide should be about 12 hours and 25 minutes later. And in this case, it was, looks like it's about 1:30. Okay, so according to the graph, it's not exactly 12 hours and 25 minutes, but close enough. So the next one then will be, figure about 12 and a half hours later from that. So if that was 1:30 in the afternoon, 12 and a half hours later would be 2 in the morning. Okay, so that was the answer, choice 2. Question 4. The time required for the moon to show a complete cycle of phases would be about 1 month. So choice 3 is the answer there. Number 5, the diagram shows the moon at 4 positions in its orbit around Earth. An observer can see a solar eclipse when the moon is at position 4. Okay, so you should be experts at that one by now. Okay, Sun, Moon, Earth. Number 6, the diagram shows the moon orbiting Earth. The moon is shown at 8 positions around its orbit. Spring ocean tides occur when the difference in height between high tide and low tide is greatest. Which 2 positions of moon will give you spring tides? The answer is position 1 and 5. Okay, and that was from yesterday's, last night's video. If you looked at it, you can review that. Number 7. The diagram shows the Earth's orbit around the Sun and different positions of the Moon as it travels around the Earth. Let's see. An eclipse of the Moon is most likely to occur when the Moon is at position B. Okay, position B right here. You can see the little moon there in front of the Earth. Alright. Actually, it's the Sun, Earth, Moon. So the Moon is behind the Earth. And therefore it's not getting... you know, it's possible for that to be a lunar eclipse where the moon is not being lit up by the sun. Okay, so the answer would be B, choice 2. And the last question, number 8, let's see, they basically want to know which of these diagrams will give you the highest high tides and the lowest low tides. So in other words, which one will give you spring tides. And I told you last night that you need the sun, the moon, and the earth to all be lined up, so that would be this one, choice 1. Okay? So that's it for today's classwork. Tomorrow's classwork is going to refer to the solar system data table that you'll find on page 15 of the reference tables at the bottom. Okay, let me just adjust this little deal here. Okay, so the bottom of page 15 will be this. And There's just a few things I'm going to go over with you here to just explain what you're going to get out of this table, and then from there you can answer all of the questions on tomorrow's handout. Okay, so actually I'll take this right off here. Get nice and close. So the first thing we have here is the particular object in the solar system that we're talking about, whether it's the sun or any of these planets or the Earth's moon. Okay, I may as well go ahead and tell you right now that there are two classifications for the planets in our solar system. They can either be terrestrial planets or Jovian planets. The terrestrial planets would be those that have more of a rocky composition and are more like what we know as planet Earth. So of course they have very different characteristics, but the other planets are going to not have rocky composition, and they're going to be much different than Earth. Okay, so these four then: Mercury, Venus, Earth, Mars, those are the terrestrial planets. And then the next, Jupiter, Saturn, Uranus, and Neptune, those are referred to as the Jovian planets, or sometimes called the gas giants. The first column here tells us the mean distance from the sun. So that's the average distance from the sun, and that's in millions of kilometers. So for Mercury, it's about 57.9 million kilometers away from the sun. Okay, Earth is 149.6 million kilometers from the sun. Okay, and you can see these numbers are increasing. So this would be the order of planets that you would find as you go further and further away from the sun. Okay, and the next column we have period of revolution. Now period means the length of time for a revolution. Okay, and if it says D next to the number, then it's telling you it's in days, and if it's Y, then it's telling you it's in years. So Mercury takes 88 days to make one complete revolution around the sun. All right, so that's basically 1 year for Mercury, is 88 days. For the Earth, you can see it's 365.25 days. Let's see. And then when we get to the Jovian planets, you see now that they're in years. Okay, so it takes 11.9 Earth years for Jupiter to go once around the sun. Neptune, it takes 164.8 Earth years for it to go around. You know, a year as we know it on Earth. Okay, so let me see here. Next, period of rotation at equator. The period of rotation at the equator would be the amount of time it takes to make one full rotation, one complete spin. And so notice, by the way, I don't know if you knew this, but the sun actually does rotate. So it takes 27 days for the sun to rotate once completely. Mercury takes 59 days. Venus, there's something interesting about Venus. It takes longer for it to rotate once than it does for it to revolve around the sun once. Okay, so that's something interesting. And then Earth, obviously, it's a little bit shy of 24 hours. Okay, and down there, the moon we had talked about a few lessons ago. It takes 27.3 days for it to rotate once, and here it shows you 27.3 days for it to revolve around the Earth once. So that's why the same side of moon always faces Earth. Next column we have is eccentricity. This was the first lesson that I showed you guys a video on, and remember, eccentricity of orbit means how oval shaped the orbit is. The higher the number, the more oval shaped it is. So of all these planets, Mercury has an orbit that is most oval shaped. It's most elliptical, okay, with 0.206. You could actually see, if you were in a space shuttle above the solar system looking down, you would be able to tell that Mercury's orbit is oval shaped, because that's enough of an eccentricity to actually detect it with your eye. But for Earth, which is only 0.017, to your eyes, that would just look like a perfect circle. You wouldn't be able to tell that that was slightly oval shaped. Okay, and next column is equatorial diameter. That's just the diameter of the planet, or the star, in this case the sun, at the equator. So for Earth, then, the diameter is, let's see, so here's Earth, and it is 12,756 kilometers. Okay, notice, by the way, that the Jovian planets, Jupiter, Saturn, Uranus, and Neptune, are much bigger. Their equatorial diameter is much bigger. Okay, next column is mass, and these numbers, these units here for these numbers, just refer to how many times more or less mass they are than the Earth. For example, let me see. So Neptune, which is right here, has 17.15. Okay, so if Earth is 1, that means that Neptune is 17.15 times more massive than the Earth. Okay, look at Jupiter. Jupiter here is 317 times the size of the Earth in terms of mass. Of course, you should also look at density for a planet. And so here we can really see evidence that proves that the, that goes along with, I should say, that the terrestrial planets are rocky and solid in composition, whereas the Jovian planets are gaseous. So Mercury, Venus, Earth, Mars, their densities are here. Okay, so 5.4 all the way down to 3.9 for Mars. But then when you go to the Jovian planets, these last four here, you can see that the densities are much lower. And that makes sense, since they are gas giants. I think that's pretty much all I need to go over, actually. Very quick. But that's all you really need for the classwork tomorrow. You just have to work with your group and use the reference tables here to answer the questions. And it's pretty straightforward. So good luck. And again, email me with any questions, and I'll talk to you soon. Okay, bye.